Hello, Mrs. Horner back, and I'm here to talk about the difference between molecular formulas and structural formulas. But I'm going to start off with an easier one than what you're seeing right here. And let me kind of cover over this at the bottom. It's kind of intimidating when you look at those. Here is an example of a molecular formula. H2O. Yeah, you know that's water. But what does a molecular formula show us? It shows two things. It shows, one, the type of atoms, and two, it shows the number or ratio, you could say number or ratio of atoms. So if we look at H2O, we know that there's hydrogen and oxygen, that's the types, and then we know it's a 2-to-1 ratio. Okay, that's the numbers. If we look at this molecular formula, we know that there's carbon, hydrogen, oxygen in it, and it's a 6-to-12-to-6, and you can reduce that to say 1-to-2-to-1 ratio. Okay, so you can see a molecular formula shows us that. But here is a structural formula. What's the one more thing that it shows here? Well, let me do water first. If we drew water's molecular formula, and you remember this from the water video, it's kind of bent because of those lone pairs in the oxygen, okay? It's a, distorted molecule, so it has like slightly positive sides, slightly negative sides. But how would we have known that hydrogens are angled like this if we didn't have the structural formula? And you can see there's angles all through this. There's even this like ring thing. Like, what's that all about? Well, that's when you learn about bond angles and stuff like that, which we don't do in here. We just kind of like look at this right now. If you get into like a massive like chemistry, like AP chemistry someday, you might learn about bond angles. But right now it's not so important. But once we know this structural formula, this shape, okay, is going to help us to understand how this molecule behaves a little bit more. So what does a structural formula show us? So we're looking at structural formulas here. We just looked at molecular formulas. They shows us still the types, still the ratios, right? Because if you count it up, okay, you can see that there's carbon in this, and there's hydrogen in this, and there's oxygen in it. And if you count it up, you could see the ratios. But the third thing, and very important, it shows us the arrangement of these atoms. Okay, and arrangement is really important because shape is so important in biology. Okay, and we're going to see how shape's important with this next term here, isomers. What we have here in this picture, okay, is three substances: glucose, galactose, and fructose. They're all a type of sugar. Okay, but here's the interesting thing about them. If you actually counted up all the C's, you would find they are all C6, and if you count up all the H's, H12, and you count up all the O's, O6. Well, how can they be all the same, C6H12O6, but yet we name them differently? Because their shapes are different. Now, I know at first glance you might look at these three and you say, oh, it's obvious that fructose, its shape is different. But what's different between galactose and glucose? There's got to be something different, because fructose, maybe you heard of high fructose corn syrup. It's a very, very sweet sugar. The second most sweetest is glucose. That's a sweetness you might find in a grape, okay? And galactose is the sweetness you find in milk. Now, when you think of milk, you don't think of it as too sweet, right? So this has like a super high sweetness, it touches your tongue, and ooh, it's a sugar high. Same with this a little bit too, but it's kind of medium. And this one is very low sweetness. So the shape of this definitely matters. But what's different about these two? If you look closely enough, this is kind of the same on this side. This coming up here is the same. Oh, by the way, it numbers the carbons. You always number them going counterclockwise. And this seems to be the same here and here. But all of a sudden you get here and you notice this comes up here, okay? And hydrogen's just down here, but here the OH is down and the hydrogen's up. That slight difference there was the difference in sweetnesses between like milk and a grape. Okay, that's crazy. This is what we call isomers. And yes, they all have C6H12O6, but they have different arrangements. And that's what we call an isomer. Now, we'll say like glucose is an isomer to galactose, but will glucose be an isomer to, say, amylose, which is another sugar out there? No. Okay, they have to have the same thing. So by definition, an isomer, and this is a definition for isomer, have same molecular formulas, I know you're thinking, what am I going to say? But different, what is it? If we look at the top of this sheet, what were we talking about? They have different structural formulas. Same molecular formulas, different structural formulas. And that's what these three are, okay? And isomers are very important because, like in medicines, for instance, ibuprofen, that's what's in Motrin or Advil. Ibuprofen has actually two isomer forms. One is actually effective in the body and the other one is not. So when drug companies, pharmaceutical companies make the Motrin or the Advil or something, they have to be sure that they're making the correct isomer form, or else it won't connect with our nerve endings to reduce the pain. So that's like one example of like why isomers are kind of important, and why drug companies can actually like manipulate the formulas sometimes to actually like work in our favor to like do something. All right. So we're still in our introduction. We talked about inorganic versus organic. Okay. We talked about the elements that are involved. Now molecular formulas and structural formulas. And now the next two things we're going to talk about are probably, two of the most important things. Okay. And not just these two terms, but the terms after this as well. Monomers and polymers. And what I'm going to pull out here and put in our video here is this. Okay, I love these beads. I talk about these beads. I pull them out all the time. And here's one bead and here's many beads. And why did I do that? Because if we look again at prefixes, okay, and biology uses a lot of prefixes. Mono means one, poly means many. So these beads are kind of modeling the difference between a monomer and a polymer. What is a monomer? A monomer is a basic unit, okay, or a basic building block, okay? The ironic thing is what we were just looking at. Okay, and let me pull that thing back for a moment. When we looked at these isomers, these are actually all monomers. So think of these as each a bead. And if we linked all of these together, then we would have a polymer. A polymer is just more than one. It's many. Okay, so it's many monomers linked together. Okay, so monomer and polymer. And remember I said in the beginning, there's going to be 4 categories. And if you look at your outline, the 4 categories are going to be carbohydrates, lipids, proteins, and nucleic acids. That's 4. They all have what we call a monomer version and a polymer version. Okay, and so keep that in mind. All right. So let me tuck these away and let's get on to like, how do we get from a monomer to a polymer? Well, that's what this next sheet is going to describe. And it's going to talk about something we call dehydration synthesis, and hydrolysis. I really wish they called this hydration, so that you could see the opposite, dehydration and hydration. But they don't, because they like to make things difficult for high school biology students by changing up the terms a little bit. But keep in mind, dehydration sounds like, you're lacking water, right? And hydrolysis sounds like you're adding water. Well, that's exactly what it is. Here's dehydration synthesis, and I'm going to pull out my beads again and show you. Like if I had 2 monomers, let me get 2 of these beads. Oh, these beads are being tough pulling apart here for me. Say here's my first monomer, and here's my second monomer. right? And remember, like if we were looking again at those isomers, right? The glucose and galactose and fructose and stuff, we would see that there's little what we call hydroxyl groups, which are OH groups hanging off of there. If we take one of those hydroxyl groups away and the H from the other one, we got H2O. Right? Take that away and it forms a bond. See how this happens? So if we remove that water, these two monomers will bond together and form like a dimer. Two means di means two. Okay. And there is a loss of water. Loss of water. Okay. That's your dehydration synthesis. Okay, that's dehydration synthesis. Now, take that dimer, and if we add water to it, so we're going to add water, then it's going to make those two things pop apart. Okay, so here's like a quick little question for you. If I have this chain that has 4 monomers to it, how many water molecules did I remove to connect those 4 beads? How many water molecules? So remember, water is removed each time you connect 2. So 1 water there. So with each bond in between, a water was removed. So how many water molecules? 3. 1, 2, 3. Okay, there were 4 monomers, but 1, 2, 3 waters were removed. So that means I would have to add 3 molecules to this if I wanted to break it down into all their monomers. Let's try another one, okay? Let's see if we can figure this one out. Let's try this one. This polymer has 1, 2, 3, 4, 5, 6, 7, 8, 9 monomers to it. So how many water molecules were removed to connect this one? There's 9 monomers. How many bonds are there? Right? And yeah, you can see it's 8. So you might be seeing a trend. Okay, so say I had another monomer that had only 5 to it. There were 4 water molecules removed. It seems to be 1 less than what the number of monomers is. And it is, okay? So dehydration synthesis removes water to connect them. Hydrolysis adds water to split them apart. Remember those 2 things. And that's it for like our introduction, these 2 videos. Make sure you take good notes on this stuff. This is like the backbone to all the other stuff. And just to give you a preview, our next video, but it's going to be in your next assignment, is going to start with the carbohydrates, okay? We'll talk about the specific elements involved, the purpose. You might not know what carbs are used for in your body already, the cell parts, and then we'll get into the monomers and the polymers. We always do these 5 things: elements, purpose, cell parts involved, monomers, polymers, and then some extra information too we talk about. All right, and that's it for these 2 videos. Take good notes, you guys, and then submit them.